Okay, so final exam for you guys is Wednesday at 1 in this room. It'll be all multiple choice, similar but not exact to the practice problems that are at the end in the last folder in Canvas. The answer key is there, so I would take a look at those. Then you can go back through your older exams, see what you missed, and then you also have all of the top hat problems and stuff you can go back and take a look at. Bobby.
I was looking at the thing at the bottom, it's all multiple choice. It wasn't letting us, it was acting weird. Like, under one with the bottom, the last page after we just cut off, and then it wouldn't let us put in.
Really?
Bottom half, you can't read it.
Did you download it first?
Yeah.
Okay. That's the first I've heard of that. So I'll take a look at that, and I'll take a look at it when I get back to my office and see what the issue is. If worse comes to worse, I'll just send everybody a copy of it, because I can attach it to an email, but I'll have to see. That's a morning class. You get the cat with the sombrero and the Jose Cuervo. Because I think it's supposed to say they said it'd be fun. Hopefully I'm not offending the sombrero wearing cat. Jose Cuervo drinking group out there. So yeah, the bottom. I'll take a look at this at the last one here. The last page is alkynes, and so we didn't make it to alkynes. So this will be starting first semester. So it's the second to last page that is relevant. So there's 66 minus the first 5. So there's a good 50 problems there. But take a look at them, because there are some things in there that you would want to look at. But I'll see. If you're having problems with it, just let me know, and I don't know what's going on here. Okay. All right. So any questions about the final exam? It's going to be comprehensive, and it will have naming. It will have SN1, SN2, chirality, all of the big topics. And it'll be probably equally dispersed. I don't try and hit any one thing harder than another.
Will it take like the full 2 hours, and how many questions?
It's going to be somewhere in the neighborhood of about 80 questions. Whether it'll take the full 2 hours is up to you. It's built for a 2-hour test. So if you're done in 20 minutes, that's probably not good. Everybody got a link to the course evaluations. All right, so the course evaluations are your opportunity, particularly the written comments, are your opportunity to tell me what you found effective, what you didn't find effective. If you have suggestions, I will take them under advisement for next semester. So feel free to evaluate, really not so much what you liked, but what you thought was effective and helped you learn. That's really what I'm interested in. But this is your one official chance to give me feedback. The same, and really kind of assess the class in the same way that I assess you by giving a grade.
At the beginning, is there on the exam, it's going to be ordered by like, exam numbers, like all the
No,
people be together and all the like, reactions be together?
No, the topics will kind of be mixed in. So I haven't had them organized all alkenes, all stereochemistry. It's going to be all mixed in.
Right, with the stereochemistry be together, like.
No, there could be a stereochemistry question. There could be a double bond question. There could be a naming question. So it's all mixed together. And that's true for the ACS final next semester. In general chemistry, they organize it by topic, but we don't. But in organic, they don't. And I haven't done that. Okay, so the course evaluation then, that's your opportunity to give me feedback. That goes to another department. In the past, we've run Qualtrics individual faculty, but this year, Todd Bruce, who's Dr. Bruce's husband, that's what he does. He's collecting all the results, and so he'll send them to faculty after all the grades are done. So I will not even know if you filled one out. Used to be I'd get a checkbox saying somebody filled it out. Not what you put down, but to do that. Because I usually provide an incentive to do the course evaluation. And my incentive would be that I will drop your lowest homework problems from the chapters. Chapter 12, if you turn in one. Now, if you turn one in, what you have to do is send me the email receipt that you get that says, thank you for completing this. So just forward that email to me, and then I will drop an additional homework problem quiz from the top hat.
I already deleted that email.
It's still there. It'll be in your trash. If not, just send me an email and say I deleted it. But that's what I will do. And actually you'll probably get it dropped anyway. So that's just incentive. Now, is that incentive for you to say, oh, well, then I just won't do the chapter 12 problems? If you want to take that as incentive to do that, I hope you have a lot of mercy. Or mercy is offered to you, because that's not the intent here. Normally, I would drop an in-class quiz, but since we only have 4 of those and you're already getting 2 dropped, 3 drops are excessive. So I figure we drop something that way for the quizzes. Or sorry, for the end of class homeworks, or the homework problems. So I will build that into Canvas. Okay. Other than that, I think if you have questions, you can email me. I will be here, except for a couple meetings next week. I think Tuesday afternoon I have a meeting. Outside of that, you can check and see my availability, but if it's not blocked off, I'm here. I will be here over the weekend in the afternoons from like noon to 5. So I'll leave the door open to the big office. So if you have any questions and you're here, feel free to stop by, shoot me an email, whatever. Okay. All right, any questions about the final? So, and if you're going to ask me, well, what do I need? You need 100. Right? I mean, you can play around with the what if function in Canvas. Say, if I get this score, I get this. I'll get this grade. And back in the day, I might have done that myself, but it's not really the way you want to approach this. You want to get the highest score you can get, and you want to push yourself as high as you can get. Because I will probably take the lines and drop them down a little bit. So you want to push your final average up as high as it'll go. Oh, that's because I haven't released it. I will release it. Yeah, I'll release it. So that's right. You can't do that unless it's available. So I will do that. Okay. And I will try and put together some more problems on naming. You will get the naming sheet that you got for the first exam. You know, that has the category, that has the priorities. You'll get that exact sheet.
Will we also get a table too?
Yes. And that should be it. Okay. All right. So that's the final. Now we have a couple topics to finish up here. And the first topic is to go back to the epoxides from yesterday. So what we said about epoxides is that we're going to add an acid to them to begin with. That's going to protonate the oxygen. Make a protonated epoxide. That looks like the bromonium ion, that looks like the mercurium ion. And so the oxygen isn't real happy with the positive charge, so it's going to push that charge down to the 2 carbons so that it can delocalize it. So this is the first step, is to protonate the epoxides, and that's all we're going to do this semester. Next semester, we'll talk about what happens if you don't protonate the epoxide. Okay. So let's say we did this reaction with H plus Br minus. So we add HBr to the epoxide. Where is that Br minus going to add? Well, we know it's going to add from underneath. But which carbon is it going to add to? Josh?
To the carbon on the left.
Why?
Because it will have the most positive charge, because it's the alkyl groups around it are sucking out charge from it.
Not so much sucking out charge, but stabilizing the charge. So where's the bromine going to add to the carbon that's most substituted? And that's the carbon with the greatest delta positive charge. So that is the carbon on the left. It's going to add from underneath so that the Br and the OH are going to end up trans. Okay, so the net result of this reaction is that I've added bromine to the carbon with the most alkyl groups, and the OH to the carbon with the least alkyl groups or most hydrogens. Now, it's not appropriate to call this reaction Markovnikov or anti-Markovnikov. Okay, that's only for alkenes. But where this is kind of relevant is, notice the positions of the OH and the Br here. Where did this epoxide come from? I made it from what functional group? I used a peroxy acid. What did I react the peroxy acid with? An alkene. I made it from that alkene. So one of the reasons why epoxides are important is because they come from alkenes, so that we can kind of think of, okay, if I wanted to add a Br to the carbon with the most substituents and the OH with the least substituents, I would go through an epoxide and add HBr to it. Now, where else have we added a Br and an OH to a double bond? Br2 and H2O. So when you add Br2 and H2O to an alkene, what are you adding? Br and an OH. How? Yes, it goes through a triangular intermediate, which means it's 100% trans, but is it Markovnikov or anti-Markovnikov? Markovnikov if you treat the Br plus as a H plus. So that means that I added the bromine to the carbon with the most hydrogens, and I added the OH to the second carbon. And that product is what? It's the opposite of this product. Right? So, for organic to be useful, particularly organic synthesis to be useful, to be able to make different molecules, which is what we need to do to make pharmaceuticals, etc. It's helpful if I can have one reaction that does one thing and one reaction that does the opposite. Markovnikov, anti-Markovnikov. 100% cis, 100% trans. And the reason that the epoxide is important is because if I wanted to add the Br to the carbon with the most hydrogens, no problem, Br2 and water. If I want to do the opposite addition, I have to go through an epoxide, add HBr to it. And then I get the other molecule. So we have the ability to do both. One can be done in one step, the other one has to be done in multiple steps, but it still can be done. Okay. So that's one example of how we can do that. I will call this sort of the yin and the yang of organic chemistry. We can add Markovnikov, we can add anti-Markovnikov, we can add cis, we can add trans. So those reactions kind of go together. So this is just an example that says, hey, Br and OH, I can add them both ways. And I can add them 100% trans in each case. Now, if I want them 100% cis, I'd have to think of another reaction.
In both cases, is the Br being treated like NH plus?
No,
Just in Markovnikov?
just in this case. Just in that case. Because when I say Markovnikov or anti-Markovnikov, I'm kind of taking this product and thinking about how we would go from here to here. So in essence, this would kind of be anti-Markovnikov, but I just said it was inappropriate to use those terms with epoxide reactions.
Okay.
Okay. We do the same thing with adding two OHs. I'll take my epoxide and I will add H plus H2O to it. Okay, my H plus protonates the oxygen to form the protonated epoxide. Again, that oxygen pushes electron density, well, pushes the charge down to the carbons. And now you're the water molecule. The water molecule is going to come in and it's going to add to the carbon with the most substituents that has the greatest delta positive charge. And those two things go together. So the water's going to come in and add there. The OH group is going to slide over to the right. And so I'm going to form that oxonium ion, and then the H plus will be lost in the final product. So I now added the two OHs 100% trans.
We have to be able to write this mechanism or just go with the final product?
Well, so how do you ask mechanisms questions on a multiple choice exam? There's many ways to do it. I could, for instance, say, here's a series of intermediates, order them. I could say, here's a series of intermediates, which one is incorrect? Or which one is correct? I could say, here's a bunch of transition states. What are they? Is they incorrect or are they correct? So you're going to have to remember this mechanism for next semester anyway, but it'd be helpful to know that, because I can't ask about it just in a multiple choice way. One thing I should ask is I should ask which way this arrow goes. That arrow right there. Because that's something that I see a lot of opposite direction answers. Use up a lot of red pen on that. Remember, the arrows are telling you what's moving, the electrons. So if the atom's leaving, so what? It's the electrons that get the arrows, not the atoms. So that's what I can do with mechanisms. So yes, you should remember the mechanisms of the things that we've done.
But what about like the ones where like you told us we don't need to know things? You won't ask us about those?
No. No, because there were some mechanisms like Wednesday that I showed you just to help reinforce the idea that things were adding cis. So I added the two OH as 100% trans. So then I come over here and I say, okay, this is the alkene that I converted to the epoxide by using peroxy acid. Can I convert that molecule into a 100% cis? Can I add two OHs 100% cis? If the answer is no, then we should learn it. But the answer is yes.
Could you use like the square intermediate and do the platinum?
I'm adding two OHs.
Is it cis hydroxylation?
It certainly is. So cis hydroxylation means add two hydroxy groups, cis. What reagents did I use for that? Either KMNO4 and hydroxide or OSO4, H2O2. So I can add 2OH as cis, I can add 2OH as trans. To add the 2OH as trans, I need the epoxide. And this is why we're talking about epoxides, because they provide an alternative sort of method to get to the compounds that we can't necessarily make directly from a double bond. So that's why they're important. Okay, so those are the two big examples, something like HBr or H plus H2O. Or remember, I could do this reaction with H2 or H plus ROH, because ROH is always a good substitute for water. I could do these reactions of protonating the epoxide first and then adding a nucleophile. Next semester we'll talk about what if I don't use H plus. But we won't do that now. Okay. So there we go. That's the use of an epoxide. So know how to make it, know what to do with it. Okay. Final topic. Oxidative cleavage. So oxidative cleavage is what it says. I'm going to add oxygens to an alkene, and I'm going to cleave the double bond. So let's start with, okay, cleave the double bond. Well, that's simple enough. Erase the double bond. Add a carbon-oxygen double bond. And there we have oxidative cleavage. I've cleaved the double bond, and I've turned each carbon into a carbonyl. So again, oxidation, add electrons, or add oxygens. Now, in order for us to understand what the full products are, we need to consider, well, what's potentially attached to each one of these two carbons. An alkyl group or hydrogen? So, therefore, we have to say, okay, I could end up with a ketone, I could end up with an aldehyde, or I could end up with formaldehyde. So, ketone, aldehyde, formaldehyde. So those are the three possibilities of products I can end up with. Now the question is, what reagents do I use? I'm going to start with KMNO4 and H+. Now what did we already see? We already see that KMNO4 and OH- did what? Added OH-. So if I'm going to come up with a little mnemonic or something to help me remember that, I'm going to remember KMNO4 with OH adds OHs. KMNO4 and H+ cleaves. Okay. So it cleaves and it oxidizes. But here's the problem. The problem is if I make these three molecules as products, the ketone is not affected by potassium permanganate. The other two react with potassium permanganate. So when I use potassium permanganate, I make ketones, but I don't make ketones and aldehydes, because the aldehyde will react with the CAMNO4 to actually form something else. So here's the oxidation reduction scheme for aldehydes, carboxylic acids, and primary alcohols. So we start with a primary alcohol, and we oxidize that to an aldehyde, which can further be oxidized to a carboxylic acid. So the carboxylic acid is the most oxidized form of a primary alcohol. Next semester we'll learn how to go back down. We'll learn how to reduce it. But this is the oxidation scheme. What reagents will take a primary alcohol? It'll actually take a primary alcohol all the way up. But more importantly, what reagents do that? You guessed it, CAMNO4 and hydrogen peroxide. Those two reagents will take an aldehyde and convert it to a carboxylic acid. Right? So when we make an aldehyde in this oxidative cleavage, that aldehyde gets further oxidized up to the carboxylic acid. That's the final product. What happens with formaldehyde? Formaldehyde, when it's oxidized, becomes formic acid. Sorry, not formic acid. Both sides of the carbon get oxidized. So this is actually carbonic acid. So formaldehyde. Formaldehyde's used, well, formaldehyde is a gas. So there's actually sort of, some carpet fibers are made with sometimes formaldehyde, and so same thing would be true for some car interiors. So you want to make sure that new carpet smell is not formaldehyde. And so there's sometimes an environmental issue there with indoor air pollution can be formaldehyde coming from things that were used to make formaldehyde. There's a lot of plastics that can be made with formaldehyde. Because formaldehyde is toxic because you usually put dead things in formaldehyde to preserve them. Although most of the stuff I think in biology is methanol. I think they got rid of formaldehyde a long time ago. So that's sort of the use of formaldehyde. It forms carbonic acid. If I didn't have water or my adult beverage in here, it would be a Pepsi. It would be a Pepsi Coke Zero, and it would be full of carbonic acid. And carbonic acid isn't very stable. What does it break down to? CO2 and water. So actually, when we oxidize formaldehyde, we get CO2 and water. Okay. So in this reaction, and there's no adult beverages. That wouldn't be compatible with my diabetes. So that's not a good combination. So when we do this reaction, we get ketones and then either carboxylic acids or CO2 and water. depending on the product that we make. Well, I have to say that because otherwise who knows what people think. Josh?
Does KMNO4 also cause it to decompose the CO2?
No. Carbonic acid just forms CO2 in the water. And the reason why that actually turns out to be important is that before next semester in lab, we're going to talk about spectroscopy for the first few weeks. And spectroscopy is how we determine the structures of organic molecules. Spectroscopy did not exist during the time period of the reactions that we're learning now. So Markovnikov or Zaitsev, they didn't have a mass spectrometer, they did not have an NMR, they did not even have an IR to analyze their products with. They would have had to exist in the 1950s. And then we would have had a bare bones IR and the beginnings of an NMR. So before instruments existed, there was a whole series of qualitative analysis tests that you had to do. So if somebody handed somebody an organic molecule or you're trying to determine your products, what you had to do was you had to do a series of color tests to determine what functional group you had. For instance, bromine is a red liquid. If I think I have a double bond, I'm going to add a drop of bromine to my molecule. It's going to add the bromines, 2 bromines, 100% trans, and the bromine orange color is going to immediately disappear. Same thing we'll find out next semester for a triple bond. So if I think I had a double bond, I'd put a drop of bromine in it. If it instantly disappeared, then I'm pretty confident that I have a double bond. If I wanted to know if the double bond was in the middle of the chain or at the end of the chain, I could use KMNO4. Because if the double bond's at the end of the chain, I'm going to make formaldehyde and I'm going to make CO2 and water. So if I did this reaction and it fizzed, oh, the double bond's at the end of the chain. If it doesn't fizz, double bond's inside the chain. So there were a whole series of those color tests that people did. And so that's why this turns out to be important. Also, people would cleave the double bonds into smaller products and then try and figure out what the smaller products are and then piece back together the original one. Unfortunately, the book has a number of those problems at the end of the chapter, which I'll talk about in a minute. How do you even approach that problem? So we're going to make ketones and carboxylic acids, or CO2 and water. All right, let me show you the other 2 reactions before I run out of time, which I haven't heard in a while, but usually sometimes people are out in the hallway going, oh, they just would have started off faster, then they wouldn't have to be doing everything in the last week of classes. I heard a very insightful student say that when they didn't know I was standing there. True. I don't feel like I'm rushed, though. Okay, I'm going to put a CH3 group there. You can put your CH3 group there. Okay, the other reagent that's more traditionally used is O3, which is ozone. So another reaction that we can use to do oxidative cleavage is ozonolysis. Okay? Biology, lysis means cleave. This is cleavage by ozone. So what happens with the ozone is, I'm going to take this arrow away. You have 2 possibilities. We can cleave the double bond. Well, we're going to cleave the double bond either way. And we're going to form that set of molecules. The question is, do I want to oxidize the aldehyde to a carboxylic acid or not? Well, ozonolysis lets me choose. So for instance, when I use ozone and hydrogen peroxide, aldehyde gets oxidized to a carboxylic acid. So I get my carboxylic acid and I get my ketone. If I use ozone and H2O2. Same products I get with caminophoric acid. If I want to leave the aldehyde intact, I can use R2S and sometimes you'll see something like zinc and acetic acid. But R2S I think is the one that's more popular. And R2S is just simply the sulfur equivalent of an ether. So if I do that, the aldehyde doesn't get oxidized. So if you want to make ketones and aldehydes, you use ozone with R2S. If you want to make ketones and carboxylic acid, you use ozone and H2O2. So that's ozonolysis. And I'm sure the book goes through the ozone is O3. It basically adds to the double bond to make another 5-member transition state, but that doesn't help us. Because once you cleave the bond, there's no cis stereochemistry, so there's no real need to know about the 5-member transitions, or 5-member compound. That's called an ozonoid. But this ozone reaction does take anything with the double bond, and it will cleave it. So there's good ozone and there's bad ozone, right? The good ozone is way up in the atmosphere, blocking out the ultraviolet light coming in from the sun so we don't fry, literally. Right? That ozone is blocking out the harmful UVCs. The bad ozone is when it's at ground level. And that happens usually during the summer on ozone action days. If you live in the Cleveland area, they tell you to basically do nothing. Don't drive your car, don't fill up your car, don't cut your grass. But the reason is because on those days you get ground level ozone form from exhaust from cars, etc. Hydrocarbons usually is the reaction. So when you have ozone, then if there's any double bonded materials in our lungs, probably not going to be good for that. If there's any rubber materials that have double bonds, over time ozone is going to basically degrade those. But this is a reaction that's been used to cleave double bonds, primarily to find pieces to put back together again to make the original molecule. So in your book, they're going to say, oh, well, here's the pieces of ozonolysis. What was the original molecule? And what you have to remember is that if it's ozonolysis in H2O2, everything that's a carboxylic acid started out originally as this aldehyde. And when you have the molecules with the carbonyl groups, those carbonyl groups were attached together by a double bond. If you do a ring, if you do ozonolysis on a ring, you basically do the same thing that we've done before, which is you erase the double bond, and you put in carbonyls. But notice that since it was a ring, it's just one molecule, because the ring holds those two pieces together. In this case, I'm using R2S, so the bottom carbon would stay as an aldehyde. And this product could either be written like this, or it could be stretched out. And let me just give you a little sort of hint on how to convert the molecule, because the way I'm writing it, I'm just imagining just erasing the bonds and putting in two COs. But if my molecule doesn't look like this in the multiple choice, how are you going to convert this to one that goes straight across? I like to number things. So I'm going to number 1, 2, 3, 4, 5, 6, and 7. Is that an IUPAC numbering scheme? No, it's just my numbering scheme. But now if I start with carbon 1 is a CH3. Then carbon 2 is a double bond. Carbon 3 is a CH2, carbon 4 is a CH2, carbon 5 is a CH2, carbon 6 is a CH2, and then carbon 7 is the aldehyde. So 1, 2, 3, 4, 5, 6, and 7. So what this can do is it can help you re-represent the molecule by numbering. Bobby? Yeah, I just didn't put the bond in. When I write them in a row, whether there's bond or not, they're bonded together. So that's how you can convert one to the other. Because I doubt the book's going to keep it in this form. And you know, always when you're converting molecules, if you put numbers on them, it hopefully will help you keep things and not lose them, or not gain extras. Okay. So if they said, hey, this is the molecule that was made by ozonolysis, the two carbonyls should go together as a double bond. And so you might just, if that was the case, what I would do is I would then go, oh, oops, overshot. There's my double bond. There they are bonded together. Now, you're not going to see that answer in top hat or on the final, so then what do? Okay, what ring do I have? I have a 1, 2, 3, 4, 5, 6 membered ring. Okay, I can deal with the 6 membered ring. 1, 2, 3, 4, 5, and 6. Just any numbering scheme. The double bond is between 1 and 6. What's attached to carbon 1? A methyl group. It's two molecules, just join them together at the carbonyls. So that's, I know there were a number of those problems at the end of chapter 12. So that is it for organic 1. It is not all over yet. It will only be all over after next Wednesday. But if you have questions on anything, either, like I said, email me, come see me. I will be around, so feel free to do that. And for the course evaluation, again, send me the receipt. If you don't have the receipt because you deleted it, email me and tell me that. And then I will program into Canvas at dropping one of the homework for those.